Welcome friends, Igor is here, and in this video we will talk about row spaces. In this lesson we will define the row space of a matrix, we will compute the row space of one matrix, then we will observe that row equivalent matrices have identical row spaces, and finally we will come up with a procedure that computes basis for both column space and row space of a matrix in one single go. Let's get started. We defined column vectors as ordered lists of numbers written in the vertical fashion, but there is nothing special about writing lists of numbers in a vertical fashion. We might as well write an ordered list of numbers in a horizontal fashion, and that will result in row vectors. The reason we worked exclusively with column vectors is that it makes the linear system notation convenient. You can think of a linear system as the coefficient matrix multiplied by the column vector of unknowns, and this is equal to the column vector of constants. Yet, each matrix has not only columns but rows, and we can work with rows of a matrix by transposing the matrix. Then the rows of the matrix become the columns. And so we are going to define the row space of a matrix A as the column space of the transpose of the matrix A. The column space of a matrix is the span of the columns of the matrix, but the columns of A transpose are the rows of the original matrix A. Therefore, even though we formally work with column vectors, informally you can think of the row space of a matrix as the span of the rows of the matrix. Let's observe right away that the column space of a matrix and the row space of a matrix are usually different objects. For example, if A is a rectangular matrix of size m by n, then the column space of the matrix resides in Cm. It consists of vectors of size m, while the row space of the matrix resides in Cn. It consists of vectors of size n. Therefore, these two sets cannot even be compared because they consist of vectors of different size. This is not a problem when A is a square matrix. In this case, both row space and column space consist of vectors of the same size, but even in this case, the column space and the row space do not have to be the same. Let's look at an example. We have a 4 by 7 matrix A, and we would like to construct its row space. So by definition, we need to take the transpose of the matrix A. It is now a matrix of size 7 by 4, and then we need to compute the column space of this matrix. The column space of this matrix is simply the span of the columns of the matrix, and therefore the row space of the matrix A is the span of the transposed rows of the matrix. In other words, it is the span of the columns of A transpose. Of course, this might not be the most efficient way to describe this span because this set of vectors might be linearly dependent, so to figure out what is the most optimal spanning set, we reduce this matrix, and we see that the reduced row echelon form contains 3 pivot columns. There are columns 1, 2, and 3. Therefore, the row space of the matrix A, which is the column space of A transpose, can in fact be described using only the first 3 columns of the matrix A transpose. Let's observe that row equivalent matrices have identical row spaces. Let me remind you that 2 matrices are row equivalent if there is a sequence of elementary row operations that transforms one matrix into another. Now, I will not present the full complete proof of this result because it is a little bit tedious. Let me just give you an idea why this result is plausible. We have 3 types of row operations, and each such operation is in a sense linear. What it does is it only creates linear combinations of the rows of the original matrix. And because the row space is the span of all the rows, transposed rows, then by taking linear combinations of vectors within this span, we do not change the span itself, because the span is the set of all possible linear combinations. So let's summarize what we learned so far about column spaces and row spaces. Suppose you're given one matrix and you're asked to find the basis for the column space and the basis for the row space. For the column space, you would reduce the matrix itself, look at the pivot columns in the reduced matrix, and take the corresponding columns in the matrix A. But for the row space, you have to transpose the matrix. And this means you have to do another reduction. You have to reduce the transposed matrix, then look at the pivot columns in the reduced form, go back to the original transposed matrix and pick the corresponding columns. So 2 spaces, 2 reductions. But we can do better than that. We can solve the problem of finding the basis for the column space and the row space by doing one single reduction. Let me explain how. This is based on the following result. There is an alternative way to find the basis of the row space. Suppose we have a matrix A and B is the reduced row echelon form of the matrix A. So we still reduce the original matrix A, not its transpose. Then we take the set of non-zero columns of the transpose of the reduced matrix. In other words, we take non-zero rows in the reduced form and we transpose these non-zero rows to produce non-zero columns. Then this set is linearly independent and it actually spans the row space of the original matrix A. I want to point your attention to one crucial difference between finding basis of the column space and basis of the row space. Remember, for the column space, you look at the reduced matrix, you find the pivot columns, but then you go back to the original matrix and you take columns of the original matrix. For the row space, pay attention to what the theorem says. You choose the non-zero rows of the reduced matrix. You don't go back to the original one. You choose the basis from the reduced matrix. So this gives us a convenient and efficient procedure for describing column and row space of the same matrix. You only reduce the original matrix A. Then for the column space, you take the columns of the original matrix, which correspond to pivot columns in the reduced matrix. But for the row space, you take non-zero rows in the reduced matrix, then you transpose them to make them into columns. Let me illustrate this technique on this example. So we have this 4x5 matrix A, and the task that we have is to find linearly independent spanning sets for the column space of this matrix and the row space of this matrix. To answer this question, we need to perform only one reduction. We need to reduce the matrix A, and we obtain the matrix B, which is the reduced row echelon form of the matrix A. Now, this is all we need to write the basis of the column space as well as the basis of the row space. So, for the column space, what we do is we look at the pivot columns in the reduced matrix. We see that there are columns 1, 3, and 5. So we take the same numbered columns in the original matrix A. So columns 1, 3, and 5 of the original matrix A form a basis of the column space of the matrix A. Still using the same reduction, we can also write the basis of the row space. For the row space, we look only at the reduced matrix, and we identify the non-zero rows. There are 3 non-zero rows in this matrix, and the row space of the matrix A is spanned by the transposes of these rows. In other words, we write these row vectors as column vectors from the reduced matrix, and this is a basis of the row space of A. If you found this video useful, and come on, I just saved you the need to do an extra reduction, then please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will finally define the central notion in linear algebra, vector space. I will see you later.